That means Abby. That means you.
Awkward.
You don't like singing about dying?
Well,
All right. Today we're going to continue with circles. This is sort of completely different from what we've been doing. So, again, more vocabulary that you have to know. But some of them are pretty obvious. For example, a central angle is an angle whose vertex is the center of a circle. Wow, how did they ever come up with a name for that? It's just like the central angle in a polygon, where the vertex is at the center.
oh my god.
There's just so many connections. Now, when you have that, it's going to break the circle into two arcs. You have an arc that goes from A to C, and then you have a bigger arc that goes from A through point D around to C. So there's two different arcs in that circle that we have shown. That little one would be called a minor arc because it's smaller. I know it's some of these are tough, but so its measure is equal to the measure of its central angle. So let's say this angle was 130 degrees, the measure of arc AC would also be 130 degrees, right? The measure of an arc isn't how long the arc is, right? The measure of an arc is kind of a measure of how much bend it has to it, okay? Now, a major arc is an arc whose points are on or in the exterior of a central angle. So its measure is 360 minus the measure of the central angle. So here, if we go back to, let's say we know that the measure of this central angle is 130, then the measure of arc ADC, notice you have to have that extra letter in there, is 360 minus the measure of AB. It'd be 360 minus 130. It'd be 230 degrees. So notice when we name a minor arc, we typically only use two letters. You can use three, like if there had been a point over here that was point E, if you wanted to say arc AEC, you can, but you don't need to. And anytime the arc has just two letters, it always means go the shortest way from one of those points to another on the circle, right? So like if I say arc CD, that means I'm going between these 2 points this way, not over the top around to D. Okay? And then last but not least, we have a semicircle. A semicircle, much like a hemisphere, and I never understood why one was hemi and one was semi. There's probably a reason for it, I just don't know what it is. But a semicircle is an arc whose endpoints lie on a diameter. It's exactly half of the circle. This is going to come up a lot, believe it or not, in problems. Not where you have to, I'm not going to ask you, what's the measure of this semicircle? But you're going to have a diameter in a diagram and you have to go, oh, I know that that's 180. Sort of like when you have a straight angle, you know its measure is 180. Same kind of thing. You use that to help you find other things. All right, see, that was page 1. So now let's actually do some of this. And, you know, the angle addition postulate and ideas like that apply to arcs just like they do to angles. So for here, for example, if I want to find the measure of arc AM, well, that's pretty easy. It's just equal to the measure of its central angle. It's 50 degrees. If I want to find the measure of ES, well, I need to know its central angle, but it's a vertical angle with ADJ. So this angle is 25. So the measure of arc ES is also 25. If I want to find the measure of arc ME, one of the things I could do, there's more than one right way to do it, is I could go, all right, what's the measure of arc AMS? 180, because it is a,
Semicircle.
yeah, it's a semicircle, because its endpoints are on a diameter. So that means that I could just take the 180 minus the 75. Notice that's also, oh, not 150, 105. Also the measure of this angle, because these three angles add up to 180. Okay, so if you're good with straight angles and vertical angles and stuff like this, you should be pretty good with this. All right, if I'm finding the measure of arc AJE, so that tells me that one endpoint is on A, one endpoint is on E, but I have to go through J before I get to E. That means it's got to be from here all the way around here to E. What kind of an arc is that?
Major.
It's a major arc. It's more than half the circle. I know arc AJS is a semicircle, so that's 180 plus the 25 for arc ES is 205 degrees. Okay, any questions about that so far? So the measure of an arc equal to its central angle, unless it's a major arc, in which case you need to, take that central angle, subtract from 360 to find the rest. Now, we've talked about congruent other things. We're going to talk about congruent arcs. Be really careful. Just because two arcs have the same measure does not mean they're congruent to each other. I'll explain in just a second. But within a circle, or within congruent circles, congruent arcs are arcs with equal measures. So it has to either be in the same circle or within two circles that are congruent to each other. And again, I'll show you why in just a second. But in this previous one, what arcs are congruent to each other? There are several. Someone give me an example. Yeah.
Arc AJ and arc ES.
Yeah, picking the lowest hanging fruit here. That means it's the easiest one. No, I'm not complaining. I'm just pointing out. That's the most obvious one, I think, at least.
Right.
There's a whole bunch of other ones, though. Yes, ma'am.
Arc JS and
Arc JS and
arc A.
AE?
Yeah.
Yeah. There's not a term for that, but I feel like those should be called vertical arcs. Right? Because they're on vertical angles.
Right.
All right. Well, those are the small ones. Let's get bigger. Yes.
Arc JME and arc.
Whoa, hang on.
O.
JME.
Okay. And arc JSE.
Wait a minute.
Wait.
Oh, arc JSE?
Yeah.
Okay. I thought you were saying RJSE, and I'm like, wait a minute. So JME, that's 180 degrees. JSE, also 180 degrees. There are two other semicircles in this. Let's add to this one. Give me one of them. Yes.
Arc AMS.
Okay. Arc AMS is one of them. There's one more semicircle in this. Yes, ma'am.
Arc AJS.
Yeah, arc AJS. And then we could get really, really big. Like, for example, arc ASJ. Is going to be congruent to arc EJS. Both of those are the entire circle less the 25-degree arc. Now, before we move on, let me point out to you why this first part is so important. Those were all within the same circle. You don't need to draw this if you don't want to. It's entirely up to you. All right. So, what's the measure of arc AB? 90. What's the measure of arc XY? Is arc AB congruent to XY? Because why?
That's why it's big.
Yeah, XY is bigger. I think of these as similar arcs. Same shape, not the same size. That helps my brain get around that. So you have to be really careful about that. Just because two arcs have the same measure doesn't mean that they're congruent to each other. They have to be in either two triangles that are congruent, or they have to be in the same, two circles that are congruent, or they have to be out of the same circle. A couple people are still writing, so I'll wait a moment. All right, let's move on. So again, in a circle or in congruent circles, these three things are tied together. If you have one, you have the other two. So if you have congruent arcs, you're going to have congruent chords, and you're going to have congruent central angles. If you have congruent central angles, you'll have congruent arcs and congruent chords. If you start with congruent chords, you're going to have congruent arcs and congruent central angles. All those things go together. I should have printed your notes in color, because I did these in color. I color-coded them. See, the congruent arcs are green, and these are green, and the chords are blue, and the central angles are red. Missed opportunity. All right, and again, it's important that they are out of congruent circles or out of the same circle. Much the same reason as we had up here. If here I've got congruent central angles, but if I was to draw in that chord and this chord, are those two chords congruent?
No.
Not remotely. Okay. All right, so here we know that chords RS and TU are congruent to each other. It says find the measure of arc RS. Well, if those two chords are congruent to each other, we know that the two arcs are congruent to each other. And if two arcs are congruent, we know that their measures have to be the same. That's one of those one-way relationships. On a personal level, you want to stay away from those, but in math, they happen all the time. Pardon?
Some life lessons.
Life lessons, yeah. Try to throw those in now and then. So that means that 3x is equal to 2x plus 27. So x is 27, and the measure of arc RS. And the other thing that happens on this, at first, you're gonna find yourself doing segments when you meant to do an arc. It's just you've done so many segments that you're trained for that. So it'll be 3 times 27 is 81 degrees. All right. Everybody good on that? All right, last page. In a circle, a radius or a diameter, because, a radius is a part of a diameter, is perpendicular to a chord if and only if, remember that means it works in both directions, it bisects the chord and it also bisects the arc. So in this picture, if we know that AB is perpendicular to CD, AB is a radius, CD is a chord, then I know that it's going to cut this chord in half and it's going to cut the arc in half. So these two are going to be congruent to each other, and these two arcs will be congruent to each other as well. Don't worry about writing this part down, but the reason why that happens is that if I fill that in and fill that in, those two triangles are congruent to each other. I know that their hypotenuses have to be equal because all radii in a circle are the same size, right? It wouldn't be a circle if some radii were bigger than others. This side's congruent to itself. And so, once again, for the second time in a week or so, why are these two triangles congruent? Hypotenuse leg. This is part of why hypotenuse leg is important. So those two triangles are going to be congruent. So now I've got all kinds of stuff that's congruent to each other. You actually can do a ton of different problems with this particular property. Here's an example. They want you to find the length of BD. And they've given you the length of AC is 1 and the length of CX is 4. And it's really easy to get bogged down on this and be like, I have no idea what to do with that. Christina knows. What should you do?
Connect XD and XB.
Yeah, you don't have to do both, but yeah, you do need to do at least one of them. Remember, sort of one of our themes this semester is if you don't have a right triangle, make one. That's going to come up a lot in this unit. And it's easy to actually get stuck at this point also. But you have to notice, if XC is 4 and CA is 5, how long is XA?
5.
So how long is XD? 5. All radii in a circle are the same length. Grace gave me that you're trying to sell me a bad watch look.
Wait, can you explain that again?
Yeah. So I know the distance from X to C is 4, and from C to A is 1. So the distance from X to A has got to be 5, right? XA is a radius of the circle. In a circle, all the radii are the same size. So that means that XD is 5 and XB is 5 also. Now, at this point, I think pretty much everyone recognizes this Pythagorean triple. What's the length of CD going to be? 3. Then BC is also 3 because a radius that's perpendicular to a chord is going to bisect the chord. So BD is 6. Now, you'll have some where you're going to have to use the Pythagorean theorem because it's not nice numbers. It's not a Pythagorean triple. Okay, so just something to get used to. Well, let's all stare. All right, any questions? Okay, your assignment is in the book.